start this reading. All right, so 5.2. What do we know? Well, we know a little bit about something called antiderivatives, and that is what you can find in section 4.10. Okay. You also might hear this called something like the indefinite integral. Okay, so antiderivative or indefinite integral are two words for the same thing. And we just talked about approximating area. And so in particular, we looked at 3 types of approximations. But we focused a lot more on sort of this idea of over versus under approximation. And sort of where do we find the values to find these, and how do they make sense with the formula? Okay. Now, what's new? All right, we're going to learn a lot of new stuff in this section. This is a very, 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 very foundational section for the last sort of 3 weeks of our class. Okay. So we will be answering a few of these questions. What is a definite integral? All right. How does it connect to area? Because we've said that word so many times, but I don't think we've really connected all the dots in the story yet. We're going to take a look at how net area and total area are similar and different. We're going to talk about something called properties of definite integrals. And then we're going to finish off this section with a theorem, the average value theorem. Okay. And in the last sort of 12-ish minutes that we have together, what I would like to do is take a look at this one example. Okay. And so we're going to go ahead and use this equation up here, this expression, and draw the corresponding picture on this graph right here. And so I've done some of that work for you already. This line in red is the 2x plus 3. Okay, so the red line in the diagram is the 2x plus 3. Now I'm wondering if you can tell me where I should start, as in what is my A, and where I should stop, as in where is my B value.
B is 4 and A is 2.
B is 4 and A is 2. Good. So we'll say right here, this is A, this is B. And so we're going to go ahead and draw some vertical lines right at A and B. Okay. And so I want to know, I see this symbol, it says integral. And so what that tells me is I would like to find the area of this shape right here. That's literally what that means. Okay, so you see this, the integral from 2 to 4 of 2x plus 3 dx. That means on the function 2x plus 3, starting at 2 and going to 4, what is the area between that function and the x-axis? Okay. Now, what shape would you say this is?
Trapezoid.
Yeah, this is going to be a trapezoid. Okay. And so if we go ahead and write that down, trapezoid, anybody happen to know the area formula of the trapezoid right off the top of their heads? I feel like the trapezoid formula just doesn't get a whole lot of love. It does look like a rectangle and a triangle. But the area formula of a trapezoid is actually very similar to the area formula for a triangle. And in particular, you have 1/2. You have something with the base times a height. But in a trapezoid, there's not just one base, there's actually two bases. And so we're going to add those bases together to find the sort of base that we're using in our formula. Okay, so instead of 1/2 base times height, we're looking at 1/2 base 1 times plus base 2 times the height. Okay. Now, most of the time when you draw trapezoids in elementary or middle school, we sort of draw them this way, right? Does that look more like a trapezoid to folks? Yeah, okay. Now, what's true about a trapezoid? Well, one of the bases is actually parallel to the other base, right? And so we might call this top one base 1 and the bottom one base 2. But what we're looking at in calculus, we actually take that trapezoid and we sort of stand it up. And so we have a trapezoid where the parallel bases are kind of vertical. We make a very special kind of trapezoid that has a right angle at one side and then the other side is sort of slanted. So all we did was kind of rotate the shape, and that gives us a trapezoid. Okay, where would I label the height on this second diagram? Yeah, this bottom part would be the height, right? In particular, this distance right here is the height of my trapezoid. And so knowing that, let's come back to this diagram where I have the two parallel bases, a height of a trapezoid, and let's fill those numbers into our formula. What would we say is base 1? Like if I call this one base 1, how long is that segment? Yeah, 7. All right. What would we say is the length of base 2? 11. Anybody get free Slurpees yesterday? I know that was a thing that 7-Eleven did pre-pandemic. I don't know if they actually did it this year. Oh, you didn't know? Yeah, so on 7-Eleven, they used to give out free Slurpees. I don't know if they're doing it this year or not. You could get like the small one. It wasn't like a big one or anything, but you could get a small Slurpee for free. So if you didn't know that, maybe they'll bring it back at another time. All right, what is the height of this trapezoid? Yeah, the height of our trapezoid is just going to be this distance right here, or 4 minus 2, which gives us 2. Okay, so now let's go ahead and do some mental math. This 1/2 and the 2, those reduce to 1. 7 plus 11 will give me 18. Okay, and so my claim is that this area right here is 18. Okay, now that's sort of one way to do it, but let's see how some of those rules from 4.1 might be helpful, or 4.10 might be helpful to find this using calculus. So this is what we call antiderivatives. All right, so let me go ahead and write the question again here. The integral from 2 to 4 of 2x plus 3 dx. All right. So one of the rules that we learned in 4.10 is something called the power rule, right? And there is a power rule for derivatives, but it turns out that there's also a power rule for antiderivatives. There's also a constant multiple rule and the sum and difference rule, and all of those you'll find in 4.10, okay? And so one of the first things that I like to do, especially in the beginning problems, is I like to write out what that power is. So like, for example, 2x is 2x to the first plus 3x to the 0. Okay. And I find this useful because if I'm going to use that power rule formula that we saw in 4.10, it's nice to know what the power is. And so the power rule from 4.10 says that you take that power, you add 1, and then in the denominator, you have that power plus 1 again. So this, when I take the integral, becomes this. Plus 3 times, we're going to use the same rule again, x to the 0 plus 1 over 0 plus 1. And this 3x to the 0 became this after we took an antiderivative. Now we have to be a little bit careful here because we have numbers on the top and bottom. We call those bounds. We're going to draw a vertical line. We're going to put a 4 at the top and a 2 at the bottom. And we're going to go ahead and simplify what we have. So this will give us 2x squared over 2 plus 3x. Let's keep that vertical line with the 4 and the 2 there. We can simplify this a little bit more. We get x squared plus 3x, and we're going to plug in 4, and we're going to plug in 2. Now, one thing that someone said earlier is that we will plug in the top number first, and that is incredibly important, okay? It's incredibly important. So we're going to go ahead and say that we're going to plug in the 4 first, and then after we're done plugging in the 4, we're going to plug in the 2. And what are we going to do? We're going to subtract these two quantities. So we get 4 squared plus 3 times 4 minus 2 squared plus 3 times 2. So this is plugging in the bottom bound, and this is plugging in the top bound. We're going to do a little bit of mental math here. We get 16 plus 12 minus 4 minus 6. And so this will give us, wow, this gives us 18. We did all of this work and we got the same number we got on the other side when we used geometry. Okay. So like many of the things we learn, there's more than one way to do a problem. And I think it's useful to sort of root ourselves in something that we know so that we can compare it to this new process that we're learning. Okay. So in this case, this area is exactly 18. All right, we could use geometry to find that, or we could use the antiderivatives. All right. Now, it would be really important this week to work a lot on your antiderivatives. Working through these problems and being able to plug in numbers accurately would be really, really helpful. Okay, just like when we did derivatives, if you put a lot of time in that front end on practicing your derivatives, it paid off a lot in a lot of the work that we did afterwards. And so this is sort of the same thing where if you put in some time and work into the antiderivatives right now, you're going to see that pay off a lot in Calc 1, but 100% in Calc 2. Okay, believe it or not, if you're taking Calc 2, something like this is going to be like the last few steps of a problem, not like the entire problem. All right, so this will be something that you'll just be like, bam, 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 done, all set. Okay, so we want to get to that point, and the way we get to that point is if we practice this quite a bit. All right. So we're going to stop the video here.